results for the school.
Oh,
Hmm. Hello. Hi, everyone. How are you? Okay. Well, the first thing I'm going to ask is I'm wondering if the sound is working. If you can see the way that this particular live stream is working, just go to type a message to chat relay, and if you can hear me, say hello. I guess asking you to say hello doesn't help because everyone is saying hello. So if you could just it is working. Very good, very good. So let me start and introduce and explain what we're doing. So first of all, I'm Po-Shen Loh, and welcome to this YouTube channel. Welcome to this live solve. We're going to be working on some problems on a mock AMC 8 which I created. The AMC 8 is a math competition which happens every single year, and well, the AMC 8 happens in January, but it's not a bad idea to try to get ready, especially if you have a winter break. Now, the easiest way to get ready is to do real problems. Sometimes people have done a lot of other problems before, so I go ahead every year and make a mock test. Now, the good news is that we have some great people to explain today. Oh, I actually won't be doing the main explaining, although I'll be giving feedback on their explanations. The reason is because the best way to learn how to solve problems is to watch people actually solve the problems. And if the guy who made up the test solves the problems, then you don't see how someone really solves the problem because I already knew how to do it. So let me tell you, we have some incredible people here today. I'm going to introduce them in alphabetical order of their first name. So let me start by saying, hey, Eli, why don't you say hello and wave, and I'll tell everyone a little bit about you.
Hello, everyone. Hope you're excited for this live solve.
Yes, this is Eli Gold. He's actually very good at math competitions himself. We have a lot of people who work with us who have done a lot of these things before. He's a 3-time Amy qualifier. He's also a USA Mathematical Talent Search perfect scorer. And he's won international and national music competitions as well for playing marimba. And he does all kinds of different things. He also does Rubik's cubing, ping pong, tap dancing, and chess. So the important thing is that people are interesting. Math is one part, but there's a lot of other things too. With that, I'll also mention we have a second co-host here today. Second co-host, I guess that means there's 3 of us all together. There's Melody Chen. Melody, do you want to say hello?
Hi.
Yes, this is Melody. Melody is from Oklahoma. I actually have had the chance to see her when I was over there. And she's also an Amy qualifier. She's also a Math Counts national qualifier. If you do math competitions in the United States, there is something called Math Counts, where one level leads to another, and at some point 4 people represent the state. And so she was representing her state of Oklahoma. But outside of math, she also enjoys playing violin and Tetris. So we have some interesting people here. I think we could make a concert with a violin and a marimba, maybe. But today we're going to do some math problems. So with that, the way we're going to do this thing is that they're going to take turns, each doing one problem, one problem. After each problem, if the other person has some comments they'd like to add, they'll add. If I have some comments, I'll add because I've made the problem. I might add some comments. But other than that, we're just going to dive in and keep going. Does this sound good to everyone? Okay. Oh, yes. People see this chat in the bottom corner of our video screen. That's how you talk to us. So very important. This is supposed to be active and fun. So if you have any ideas, send messages to chat relay. There's a moderator here, and they'll make sure that bad messages don't get through, but you should join in and share all of your ideas as we go. So with that, let's start with, again, alphabetical order by first name. Eli, why don't you go and take off with question 1?
All right. Okay. So I think we were going to look quickly at an icebreaker first, just to get us started, get us
Good idea.
comfortable talking in the chat and everything. So first, how many holes are in a straw? And if that's too easy, maybe we could ask how many holes are in a t-shirt. And I am really loving how much stuff I'm seeing in the chat here because this is kind of amazing, seeing so many people engaged. But first, how about Melody? What do you think about this question?
Yeah, like a lot of people in the chat, I have always believed that a straw only has one hole. It's like a very long hole, but like you can look through it and it's just one. You can't count two, really. Oh, and then, but a lot of people are saying differently for a t-shirt. Eli, what do you think about a t-shirt?
Oh, I'm gonna try to draw a T-shirt. This is maybe a mistake, but I don't know. I mean, I feel like if your reasoning is that a straw only has one hole because it kind of just swished down into a donut, then if you try to do the same kind of thing, I see a lot of people in the chat saying, well, either 3 or 4 for a T-shirt. But the thing is, like, couldn't I just have one hole here and then like one hole along the arms? I feel like there's at most 2. Maybe there's like a really weird hole that's like one that goes through all of them. I don't know, but I feel like there can't be more than two. But a lot of people are saying 3 and 4, so maybe there's some other way of viewing it that I don't see. Oh, I see some people saying that they do topology in the chat, so maybe the topologist can help us figure it out.
I definitely can't see three. I can see the reasoning for four holes, but like if you use the same reasoning as there's only one hole in the straw, there's only one hole in a t-shirt. It's just a big one that has many like it could go out to four places.
Yeah, I think that that's reasonable. I don't really see where the 3 is coming from. Maybe someone can explain. But I think we've discussed the holiness of straws and t-shirts. Maybe we should go to something that's even more holy, which is the AMC 8 mock test. So with that being said, let's go to question 1. What is the units digit of 1 times 12 times 123 times 1234 times 12345? I could have said 1,234, but that's kind of long. So I think there's two ways that you could approach this, and I see a lot of people in chat saying 0. And the first way that I kind of see is, well, I see something that ends in 5, and things that end in 5 are really nice to multiply by because I know that at the end I'm only going to be left with something that ends in 5, right? If I have something that ends in 5, I multiply by something else. You know, if I have like a 1 at the end here, then I'm going to get a 5. If I have a 2 at the end, then I'm going to get a 0 and a 1 carries over. Not there. And so I know that I'm either going to get a 0 or a 5. And since I have a 12 here, I know that this is actually going to be even. So I can't end in a 5, which means I have to end in a 0. And so that looks like option A to me. But another way that you might think about this is, well, actually, I don't really need to like actually multiply all of this out to find the last digit. I can just look at the units digit of each of these individually. And Melody, why might that be the case?
Yeah, so when something asks for just the ones digit at the very end and you're multiplying things, the really big numbers at the beginning, like 10,000 something, it doesn't really matter. Only like the last digit of each number matters when you're looking at the ones digit. So you could just do 1 times 2 because the last digit of 12 is 2, times 3, times 4, times 5 to find the last digit. And then you can see there's a 2 times 5, which makes a 10, and everything times 10 is 0. So you also get 0.
Indeed. So, Professor Loh, do you have anything to add about this one?
Yeah, well, I'll just say that was roughly what I was thinking about. It's a good first question, and indeed what you did is exactly what I'd do too. Thank you. With that,
Awesome.
on to the next one. Let's go, Melody.
Oh, okay. Question 2. Express this as a decimal. 1 over 8 minus 1 over 40 plus 1 over 200. So I just have a preference in math. I prefer to work with fractions instead of decimals because they just seem simpler to me. So I would make everything over 200. So then I can see that 8 times 25 is 200. So the first fraction can become 25 over 200. And that's the same as 1/8. And then the second fraction, we can multiply the bottom by 5 to get 200. So we also have to multiply the top by 5. So we minus 5 over 200. And then just add 1 over 200. So this gives us 21 over 200. And making something over 200 into a decimal is actually pretty easy because a decimal is just something over 100. So we just divide the top by 2 to get 10.5 over 100. And that as a decimal is 0.105, which is A. That's just kind of a personal preference of mine. And I'm sure there's another way to do this where you don't have to work with.
Yay! Yeah, that sounds good. I think that looks like what everyone is doing here. That sounds good. I think this particular one, there are many ways to do it. I think I might have been thinking of doing it with decimals, but I think that what you did is just as efficient. So good for you. Let's go on.
Okay. On to question number 3. What is the area of the shaded region here? All right, so we're given some lengths. This is 3 and 3. This is 3 and 4. This is 4, and this is 3 again. And I think there's probably quite a few ways that you could do this. I'll do the kind of interesting way first, which is to look at the whole thing and then subtract out these little squares in the corners. So if I take the whole big square, then or I don't know if it's a square, but it's a thing. I will find out that it's a square. This is 3 plus 4. So that looks to me like a length of 10. And then it's the same here, right? It's 3 and 3. The 4 is in a different place, but that doesn't change anything. So they're both side length of 10. Ooh, don't really have space. That's okay. And so if I do 10 times 10, that'll give me the area of the whole thing. So that looks to be 100. But now I have to get rid of the stuff that I don't want, which is this stuff that's not shaded. So this stuff over here. And it's not too bad because these are just a bunch of rectangles too. Because I have a 3, this is also a 3, so this looks to be 9. This would also be 9. But then over here, this is of length 4, so this would be 3 times 4 and 3 times 4. So looks like the stuff that I don't want is 9 plus 9 plus 12, which is, okay, here we go. 18 plus 12 is 30. 30 plus 12 is 42, I think. Oh, I can't do this math. This is the hardest part. So 100 minus 42. And I believe that should be 58. Oh, yay. That looks like option D. So looks good to me. But maybe there's another way we could do this, Melody?
Yeah. So my first instinct was just to add up the yellow stuff. I think it would be easier if we divided it into 3 sections, like drawing a line here and a line here. So this big rectangle in the middle, like Eli said, this whole length is 10 because we can bring the 3 down here and see that it has a length of 10. So then 10 times 4, this middle section is 40. And then we can get the small sections on the top and the bottom. So the top one has a length of 3 and a height of 3, so this is 9. And the bottom has also a length of 3 and a height of 3, so it's also 9. So 40 plus 9 plus 9 also gives us 58. So that double checks our answer. And I think it's correct.
Cool. Yeah. Maybe I'll add another another way. So these are all good. I'll tell you what I was thinking about when I was doing it. I can't draw, unfortunately, because I don't have the same setup as you guys do. But if you imagine that those rectangles, the little rectangles, are movable, you can push them all into the lower left corner. If you push them all into the lower left corner, they make a rectangle. And then what's left, the yellow stuff, is just the difference between a big square and a smaller rectangle. Can one of you help to illustrate this? I think you probably know what I'm talking about.
Yeah, I think so. So, yeah, okay, Melody, you can try.
Well, oh, I was thinking, so you move this kind of blank part down here instead. So there's, oh, I can't find my pen. Oh, so there's like the 3 here, kind of. And then you move this part in and this part in. So there's another length of 4 here. Oh, my lines are not very straight, but there's another length of 4 here and length of 4 here. Is that what you were visualizing?
Yes. Now see what happens.
Oh, okay. Eli, do you want to take us through this part?
Yeah, so this is everything that we don't want all in one corner, and it's a nice rectangle. So this is 6 and this is 7. The area of what we don't want is 42, 6 times 7. And then the area of everything that we do want, we said before, was 100, 10 times 10. And so we get 100 minus 42, which is indeed 58 yet again. So we have 3 different ways of doing the same problem.
Yeah, that is great. Okay, well, so thank you. Again, what you guys were doing is totally fine too, totally good too. I also see that people are saying it's blurry. So in that case, I think what we'll do is we'll, make the person a little bigger because right now, I guess we wanted to show a lot of people talking. But with that, let's continue on to the next question, question 3. I guess that's Eli.
All right, question 4. What is the product of, okay, we're given that the product of 4 distinct integers is 4. What is their sum? Okay, this is interesting. So we have something like a times b times c times d is equal to 4. And a, b, and c, and d are all integers. And we want to know the sum of all of them. And what's kind of weird here is that, it might not actually be possible to find such integers. And it maybe is possible that there's more than one sum. So we have these interesting options, d and e here. But I wonder if we can see if there actually is only one way to do this. What's nice about 4 is it can really only be written in two ways, like 1 times 4 or 2 times 2. But we're allowed integers, which can be positive or negative. So these aren't really the only ways to do this. And so I think also a key thing is that they're distinct. So we can't just have like 1 times 1 times 1 times 4. So let's just see, well, are we able to use a 4 anywhere here, like a +4 or a -4? Well, if we had a 4, then, okay, well, we would have to have the rest be 1s, because they can't be 2 or bigger, because then we'd be too large. So they can either be 1 or -1, and that means we have 3 things. We only have 2 options. You could say the pigeonhole principle or something. We definitely can't have them all be distinct, right? We can only use 1 or -1, so I don't think this is ever going to work, and it's going to be the same with -4 as well, because again, we can only have 1s and -1s. So eventually, we're going to have a repeat, and they can't be distinct. So I think we can't do this whole 1 times 4 thing, and instead we have to do a 2 times 2 type thing. But of course, we can't have them both be 2, because those wouldn't be distinct, so probably we'll have 2 and -2. And hey, well, this is actually very nice, because once we have this, this is -4. And in order to get rid of that negative sign, I think the only thing we can do is have a 1 and a -1. And wow, that looks like not -4, -1. And it looks like those are 4 distinct integers whose product is 4. And, well, since they're just negatives of each other, their sum is 0. 2 plus -2 is 0. 1 plus -1 is 0. So that looks like option A.
Yeah. Ah, interesting. Somebody asked, how do you know there aren't more answers? I think that's pretty good.
Melody, you want to answer that?
Oh, sure. So I think Eli pretty much went through all the possible choices, but I can go more in depth on that. So we know that we can't have anything greater than 4 because they're integers. And if you went to like 8, you'd have to have half to cancel it out, and that's not an integer. So our only possible options are something to do with ±1, ±2, or ±4. And as Eli said earlier, we can't use ±4 because then we could have, let's just use 4 as an example. Then the rest would have to be some form of 1, but we only have +1 and -1, and we don't have a third 1 we could use. So we can't use 4 in there. And then we found the option with the 2's, and there's no option with just all 1's either, because we only have 2 of each type. And we have to make sure that we have an even number of negative numbers so that it'll become positive at the end. So I think that kind of just takes out all of our possibilities. So we know that it's our only one. And that answer choice actually really freaked me out too, because usually I like these kinds of questions because there's only one way to do it. Because, well, there's only one sum usually, but then there's the answer choice. There might be more than one sum, so you definitely have to double check that. And that was a little bit trickier.
Cool. Sounds good. Let's go on.
Oh, this question is pretty cool. Okay, so this one says, in the United States, coins are worth 1, 2, 4, 8, 16, 32, or 64 cents each. So what is the fewest number of coins that can total exactly 63 cents? So if we want the fewest number of coins, we want to use as many large valued coins as we can. So we want to make 63 cents. We can't use the 64-cent coin because it's too big. So I guess the largest coin value we can use is 32. So if we use a 32-cent coin, that gives us only 31 cents left. So we can't use another 32-cent coin. And then we keep running into that problem. So after we get to the 31 cents left, we use a 16-cent coin, and there's 15 cents left. So we kind of keep going. So it'll eventually go, we'll use a 32-cent coin, then a 16-cent coin, then an 8-cent, then a 4-cent, 2-cent, then 1 cent. And that'll add up to 63. Like Eli put on his screen. That's very helpful, actually. Oh, I'm sorry, I forget you can't see Eli. So it's just 1 plus 2 plus 4 plus 8 plus 16 plus 32 equals 63. So that's the perfect amount. Too bad we can't just use the 64-cent coin. But so now we have to count how many coins there are. So 1, 2, 3, 4, 5, 6. We have to use 6 coins to make 63 cents perfectly.
Yes, and I did notice that some people in the chat were referring to binary, and that is kind of exactly what this is, because we're given denominations that happen to be powers of 2, and so it's essentially like a representation of a number in binary because, well, we wouldn't want to use two ones when we could use a 2 instead, we wouldn't want to use two twos when we could use a 4 instead, and so on. So we're only going to have either one of them or zero of them. And so it's kind of like a representation in this case of 1, 1, 1, 1, 1, 1 in binary. And so this is indeed the number 63, and some may recognize that this is one less than 1000000, which is 64 because it's 2 to the 6th power. And so if you wanted to be sneaky with this a little bit, you could happen to notice that, well, 64, nicely in binary, is 1000000, so subtract 1 to get 63, and that's all ones, which means I have to use all 6 coins.
Cool. And I will also say there was a typo, I think, in the sense that when I wrote the problem, you might know that the United States does not have coins worth 1, 2, 4, 8, and so on, which is a big shame. We probably should. But actually, it was supposed to be called the untied states. The I and the T are supposed to be flipped. But anyway, in case you were wondering, how come the United States is so strange? It's because those are the untied states. All right, with that, let's go on to the next question.
All right, so question number 6. We roll a standard 6-sided die 3 times, and we want to know how many different numbers are possible as sums. Okay, this doesn't seem too bad because we can just, get up to 6, up to 6, and up to 6. And so, I mean, the biggest that we can possibly get is just 18, which is 6 plus 6 plus 6. And the smallest that we can get, well, that should be 1 plus 1 plus 1, because we don't start at 0 on the 6-sided die. And so that would be 3. And we can definitely get everything in between. Actually, we can get everything in between several times, like in several different ways. For example, to get 4, you could have 2 1s and a 2. Or to get like 15, there's many, many different ways you could get that. So I think we can definitely get everything in between, which means we just have to find how many numbers are there from 3 to 18. And, well, there's a lot of ways that you could do this. Maybe you know a formula for this or something. But the way that I like to do it, just subtract 2 from everything. And it's the numbers from 1 to 16. There are 16 numbers there. So it looks like option B.
Cool. That sounds good. Let's keep going. We got to catch up on time.
I see.
Oh.
Okay.
I'll go super fast. Oh, I actually really like this question. There are a lot of big numbers, but basically we start with this much money, we add this much money, and we take out this much money. So it's just an estimation problem, I guess. So, let's see. We start with $3 million and we add a couple of 20,000s, which doesn't really matter to us because we have $3 million. And then we take out, this looks about 400,000. So let's just say this is about, oh yeah, about 400,000. And then we put in about 500,000. So, oh, actually, let's look at the 20s because some of our answer choices are a little bit close together. So this is about 520,000, I think. And then we start with $3,500,000, and then we add 500,000 and then subtract 400,000. So if we just looked at what we add and what we take out, there's like a net gain of about $120,000. So, oh, I think, can you guys see my screen? Oh no.
Oops, 1 second. Yeah, there we go. We're back.
Okay, perfect. So we have a total gain of about $120,000, and we want to add that on top of our $3,500,000. So, Oh, I'll move to the, oh, sorry. There is not another slide. So we have about $3,500,000. And then we want to add just 120,000. So that gives us about 300 or 3,600,000. Is that one of our answer choices? Yes, it is. Okay, perfect. So this problem without the answer choices would have been very painful, but luckily we do have answer choices. So we can see that our closest one is 3,600,000. And the next closest one is 3,400,000, which we know is actually, it's pretty far. So we can be pretty sure that this is our answer, just with a little bit of estimation.
I know
Cool.
that we're
You
supposed to
asked
be
something.
going. Yeah, I did want to just mention something that you could do to check your answer quickly because I think B and C are, fairly close if you were just trying to do this really quickly. So one thing that you could do is just look at the last digit of everything because I start with a last digit of 8 and then plus 5 plus 4 plus 5 and then minus 1 minus 0. And then, well, it's just some tricks here. 5 plus 5 is the same as 0, last digit of 0. 4 plus 8 is 12, so it's like a last digit of 2. Minus 1 gives us 1, and this indeed does end in a 1, so we can be pretty confident. The other one that ends in a 1 is like 4,400,000. That's way too big, so looks like option C to me.
Cool.
And, all right, we can go on to question number 8. What is the smallest positive integer formed from consecutive ones whose square contains the digit 0? All right, this is fun. If you haven't played with a calculator squaring 1, 1, 1, 1, 1, 1, it's a fun thing to do. You may get some enjoyment out of it, but we're going to see what happens when you do that right now. So you probably know what 11 squared is. It's 11 times 11, ends up being 121. 111 times 111. Okay, we might as well just actually write out the calculation. This is like 1, 1, 1. Okay, and then nothing, 1, 1, 1. And then nothing, nothing, 1, 1, 1. And okay, I think you might see what's going on here. This is going to be 1, 1 plus 1, which is 2, then 3, and then 2, and then 1. So 1, 2, 3, 2, 1. 1, 2, 1, 1, 2, 3, 2, 1. Can you guess what the next one would be? Maybe 1, 2, 3, 4, 3, 2, 1. And indeed, that's exactly what's going to happen if you just write out the sum again. Like 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and 1, 1, 1, 1. Slightly incorrect overlapping, but that's close enough. So, yeah, that's very incorrect. I have to fix it. Okay, this is over here. Okay, this overlaps here. There we go. Okay, you can see that this is 1, 2, then 3, then 4, then 3, and then 2, and then 1. And so this pattern will obviously continue up to 9, right? Because I can have 9 digits long. I'll get 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, 7, 6, 5, 4, 3, 2, 1. But then something's going to go wrong when I have 10 ones, right? If I have 10 ones in a row, then I'm going to get 1, 2, 3, 4, 5, 6, 7, 8, 9, and then that's supposed to be a 10. There's going to be 10 ones that are lined up. And if I add them together, I'm going to get a 0 and then carry the 1. And then actually the next one will be 9 plus 1, which is 0. And then I'll carry the 1 again. And then I'll get a 9. And then it'll be a 7, which is kind of weird. But no matter what, I'm definitely going to get a digit 0 in there, but never before with 9 ones or 8 ones or anything. So I think I can be pretty confident that whichever one has 10 ones will be the first time that I get a digit 0. And now it's just a counting game. It can get kind of confusing, but I know that this has 9 ones, right? Because there's 3 groups of 3, so this one probably has 10, and that looks like option D to me. And I think that's probably the right answer. Awesome. Okay, on to question number 9.
Oh, a long question. Okay, so your house is 10 miles from your friend John's house, and John's car is 12 miles from their house. John is exactly 1 mile from his car, and M is the maximum possible distance John is from your house, and M is the little m is the minimum possible distance. What is M plus M? Okay, so this problem is just asking us to find two possibilities for where John is. So if you really like him, you want him really close to you, and if you really don't like him, you want him very far away from you. So let's pretend we don't like him first. So the problem says that your house is 10 miles from John's house. So this is me, okay. And then 10 miles from John's house. Let's say this is about 10 miles, and this is John's house. if we want him as far away as possible, then we want the 12 miles that John's car is from his house to also be in this direction. So let's say this is 12 miles, and this is John's car. And then the problem said that John is 1 mile from his car. So let's just say this 1 mile is John, 1 mile. So I think this is like the furthest John could possibly be from us. So that would be 10 plus 12 plus 1 is 23 miles, I think. So 23 miles is the furthest he could be. But what if we really like our friend John? Then we want him to be pretty close. So this is us again. And then his house still has to be 10 miles away from us. We can't change how far his house is. So this is 10 miles. But for John to be closer to us, we can put his car on the other side of us. It's still going to be 12 miles from his house. But his car could be 2 miles away from us. And since the house is 10 miles away from us, it's 12 miles total. So then we have John, which is 1 mile from his car. And we want him to be very close to us. So right in the middle, we have John. Oh, let me rewrite this. So this is going to be 1 mile on this side and 1 mile on this side. So John is right between the car and us. So in this scenario, John is 1 mile away from us. What did the problem ask for? Okay, so the maximum distance is big M, so that is 23. And the minimum distance is little m, which is just 1. And big M plus little m is 23 plus 1 equals 24, which I think is our answer, probably.
I actually had a question about this one because I guess this is assuming that they're all on like a straight line, right? That it's just like one road. Because I think if you allowed, a plane, then the car could actually be, somewhere over here. And then this could be a distance of, oh no, that doesn't work because this is actually further away. No, I see what's going on. Never mind.
Yeah.
Sorry.
I'm glad that you brought that up because you can't assume it's on a straight line. Yeah, it's not on a straight line, but it works even though it's on a plane.
Yeah, because it's actually as close as you can possibly get over here, and then this just gets you closer. So this would actually be further away. Never mind. On to the next question. Great job, Melody. Question number 10. Point X is at -2, 0. Point Y is at 2, 0. And the eclipse is centered at 1, 1. Which of these points will make the largest area triangle together with X and Y? So like this triangle, this triangle, this triangle, and so on. I don't even know if we need to draw out the whole coordinate system, but it might be nice to just figure out where our bearings are. If this is -2, 0 and this is 2, 0, then, well, this would have to be in the middle between them is the origin. So it's like here. And then I'm going up and over 1. So this would be this point here where the center of the ellipse is. But I'm not even sure if any of that really matters. All we want to know is which of these points will make the largest area triangle. And, well, I mean, this can be kind of confusing if you're just trying to do it by sight, because, like, okay, this seems like, a tall triangle, but this is a long triangle, and this is a long triangle, so maybe those have a larger area, but I think it's actually not a good idea to, visual here. Distance here, and it's pretty clear that this is going to be smaller than the distance from A, and then to D this is going to be really, really short, so this is going to be an even smaller area. And to B, I can definitely tell that this will be smaller than from A, and I guess this is where we can use the fact that it's centered at 1, 1, so this is below the center. And then similarly for C, this is going to be a very small height as well. And so I think I can see pretty clearly that A is the largest height, and of course all of the bases are the same, so that means that 2A has to have the largest area. So looks like option A to me. All right. We good with this?
Great.
Cool. On to question 11.
Cool. You have exactly twice as many dimes as quarters. What is the average cent value of the coins? Okay, so we're in the real United States now. And what I like about these problems is it might look pretty complicated because who knows how many coins you have? You could have 4 dimes and 2 quarters, or 20,000 dimes and 10,000 quarters. But actually, it doesn't matter. I really love just putting in random numbers here because they all give you the same answer. So let's make it as simple as possible. You have 2 dimes and 1 quarter. So let's write that down. So if you have 2 dimes, then that's 2 times 10 cents total. And then 1 quarter is 25. And you want the average of the coins. Well, you have 3 coins, so just divide this all by 3. Equals 20 plus 25 over 3, which is 45 over 3, which is 15. So the average cent value of all these coins is 15 cents. Oops, I completely missed that circle. But it's 15 cents.
Yeah, looks good to me. All right. On to question number 12. Oh, the long question. Here we go. This is some essay practice. A 13-member city council is deciding whether to approve 2 new rules. Okay. Each person has 1 equal vote, so 13 people, 1 vote each, and it must be either yes or no. They can't abstain or anything. The first new rule would make littering illegal and requires at least half of the council to vote yes in order to approve. Okay. The only important thing from that sentence was the half, so I'll circle that. The second new rule would establish a 10-year limit on terms for the council, disallowing any individual person from serving on the city council for more than 10 total years, whatever. Since the second rule concerns this council's own operation, it requires at least 2/3. Okay, that's all I care about, the 2/3 to vote yes. Both new rules end up being approved. Okay, great. What is the largest possible fraction of council members for whom the number of yes votes they cast was exactly 1 out of 2? Okay, so this is a very confusing question in terms of what it's actually asking, but it's basically saying, there's a lot of different ways that they could pass both of these, and across all of the different ways that these 13 people could vote, which one has the smallest, or the largest possible fraction in which they only said for yes for one of them, like out of the 13 people. Okay, so here we go. I think the way that I would approach this is with just drawing a nice Venn diagram. I like Venn diagrams. So here we go. This will be the 1/2 Venn diagram, and this will be the 2/3 Venn diagram. And first, I guess we should just say, like, what actually means, what do we need to get half of the 13-member council? Well, since I need to get at least half, 6 won't do it because 6 times 2 is 12, which is too small. So I'm going to need at least 7 in here. And then for the 2/3 one, well, 2/3 of 13, like 26 over 3, it's like 8.6 or something. So I'm definitely going to need at least 9 because 8 would be too small. That would be like 24, and I need to get 26. So I need at least 7 in this one and at least 9 in this one. And I'm trying to maximize, or excuse me, I'm trying to minimize the ones that are in here, right? Because we want everything that's out here. These are the ones for which they only cast 1 out of 2. And this is the ones for which they cast both yes to both of them. And I guess the ones that are outside of this are the people that didn't say yes to either of them, but I don't really care about those. So the question is, how can I minimize this region here so that I can maximize this region over here? And so I guess we could just try putting in some numbers. Like, can I make this as small as 0? Can I have all 7 and all 9 over here? Well, no, because I have a 13-member council, so that would be too big. I would have 7 plus 9, that's 16 people. That definitely doesn't make any sense. So can I have this be 1? Well, if it's 1, then I need at least 6 over here, and I need at least 8 over here, right, in order to get 7 and 9. And again, this would be too many because 6 plus 1 is 7, 7 plus 8 is 15, and I only have 13 people. So, I can try 2, then I'd need 5 and 7. That would be 14, still too big. And so then I can try 3. And here it works, because at 3 I can have 4 and 6. 6 plus 4 plus 3 is exactly 13. And so what's the total number that are only 1 out of 2? That looks to be 6 plus 4, which is 10. 10 out of 13. And that's whatever option it is. I don't have the options on my screen anymore. But yeah, looks like option D it was.
Yeah, yeah. So it's interesting the way you did it. You were trying to sort of push them apart as far as possible. You can also you can get that last part with inclusion exclusion instead of guessing too, because you have a 7 and a 9, I guess, and that adds up to 16. But there's like 13 spaced altogether, so that means the overlap would be 3. But yeah, this is good.
Oh, this next problem is pretty cool. It's another estimation one. We've got these very big, very random numbers, so they're very hard to work with. So we see a circle, and it basically wants us to find what fraction is this yellow thing of the big C3 circle. So the problem is these numbers are very ugly. We do not want to square these. But luckily, the answer choices are pretty far apart, so we know we can just estimate and hope. So I think our first step should be to find the area of the yellow part. So hopefully this is not as hard as it looks. So we know that the radius of the second circle is about 7,500. And then the radius of the first circle is about 2,500. So we can find the area of the second circle and subtract the area of the first circle to get the yellow part. So let's just say this is about 7,500 squared times pi minus about 2,500 squared times pi. But another interesting thing is, since we're talking about percent of the area of the circle 3, the pi doesn't even matter because there's pi in everything. So we can take the pi out of everything because we're going to put it over it in a fraction anyways. So let's just ignore the pi's because they just make everything harder to work with, sadly. I am a big fan of pi, but not today. So now we have pretty much the area of the yellow part. So now we have to put that over the area of the big circle, circle 3. So that the radius is about 10,000. So let's just put that over 10,000 squared. So let's split up this fraction so it's easier to work with. So if we have about 7,500 squared over 10,000 squared minus 2,500 squared over 10,000 squared, this is about 3/4. And this is, oh, I forgot the square. And that's about 1/4. So let's just say that is 3/4 squared minus 1/4 squared. So that's 9/16 minus 1/16, which is 8/16, which is just 50%. I think that was option C. Oh, there we go. Okay, 50%, option C. Perfect.
Cool. One thing, for some reason, Eli, your audio seems to be a little bit out for us. I don't know, Melody, did you hear Eli?
Oh, no, I didn't.
Yeah, so Eli, you check your audio. Can you say hello real quick, Eli? Melody, are you with me in that there seems to be a
Oh,
slight issue with the audio?
yeah, I can't hear Eli either.
Okay, so let's do this. Eli's going to figure out his audio. While he figures out, and Eli, as soon as you figure out your audio, just like jump in and say hi, because then we'll hear you and we'll know the whole thing is okay. But in the meantime, I'll just make a little comment about this question. So this question is like, if you think about making a circle by putting together a lot of rings like an onion, then in some sense what we've got here is we've got a bunch of the middle of the circle, from the middle of the from like the middle radius, and we got basically half of the different radii in the circle equally balanced around half the radius. And that's actually why the answer is half. It's because if you made a lot of rings and put them all together to make a circle, we effectively took like the middle rings and half of them. So that's why that works. Yeah. Meanwhile, Eli, do we have audio yet or no?
Can
Hey,
you
I
hear
hear
me
you.
now? Yes.
Yes, we can hear
Okay.
you. Come back in.
Awesome. Now we can move on to question number 14, which
Your
is what I was
volume's a
saying
bit
before,
down.
but you know.
Yeah.
Oh, okay. I see.
Maybe just be a bit louder.
Okay, I can just scream a bit. That's fine. Hello. What is the sum of the prime numbers which are factors of 111, 111, 111,111? All right. Here's something that's fun to notice about this. I have 111, and I have it, twice. But actually, that means that I can factor this number because this is 111,000 and 111, as I said in just naming the number. But this actually makes it really nice because this is 111 times 1,000, and this is 111. So this means that I can factor out the 111, and I get 1,001 over here. And so, well, now I just have to factor 111 and 1,001. And this isn't actually too bad. If you happen to notice that 111, 1 plus 1 plus 1 is 3. You use the fancy divisibility rule for 3. I can guess that this is divisible by 3, so I can look at 111 divided by 3. It seems to be like 3, 9, 2, 1, 7. So 37. So that looks like 3 times 37. Hey, those are already prime. Looks like I'm on the right track. And now I just have to look at 1,001. So if I take 1,001, and if you use the divisibility trick for 11s, if you want to call it that, 1 minus 0 plus 0 minus 1 is 0. So that's divisible by 11, which means I can guess this is probably divisible by 11 as well. And if I go through that, well, 11 goes into 100 9 times. This would be 99, and 1, 1. So I get 91. And so looks like I get 11 times 91. 91 can actually factor again because I can just notice that it's divisible by 7. If you happen to see, maybe it's like 70 plus 21. So also there is a divisibility trick for 7s. It would be 9 minus 2 times 1, which is 7. That's divisible by 7. Anyway, so 91 happens to be 7 times 13. So I have 7 times 13 times 11 times 3 times 37. And those are all of the primes. So maybe I should, write them next to each other. Times 7 times 11 times 13 times 37. I think that's all of them. Now I just have to add them together. So 3 plus 7 is 10, plus 11 is 21, plus 13 is 34, plus 37. Okay, wait, 34, 37. I can't do this in my head. Let's see, that'd be 60 and 11, 71. Okay, option A. Looks good to me. And we're right. On to question number 15.
Yay!
Okay, so John has a calculator that does something super cool, and it just multiplies the number by 2 and adds 1. So if you put 5 in there, you multiply by 2 to get 10, and then add 1 to get 11. So John puts a number in there, and he presses that button 6 times. And then at the end, it shows 63. And this question wants you to figure out what the number was originally. So I think we can just go backwards. If we start with 63, and let's write down the original operation. So 2x plus 1 equals 63. Oh, it's not writing. It's okay. 2x plus 1 equals 63. So then to get to the original step, we have to subtract 1, so get 2x equals 62, and then divide by 2 to get x equals 31. So we go backwards, and it's 31. So now we know the process for going backwards. Subtract 1 to get 30, divide by 2, that gives us 15. I'll stop drawing the arrows because they take up too much space. But 15 minus 1, we get 14. Divide by 2, we get 7. And then we can do the same thing again. Minus 1 to get 6. Divide by 2, 3. And then we get 1 and then 0. And then we can keep going, but we don't need to. So now we have to make sure we don't pick the wrong number. So we know that when we get to 31, this is our sixth press of the button to get to 63. This is the fifth press, the fourth press, the third. Oh, did I count wrong? Uh-oh. Okay, the sixth press, the fifth, the fourth, the third, the second. The first press was on 0. So we started on 0, and then we pressed it once and got 1. So just to make sure, the answer is 0. Because this part, it's very easy to get off by 1. It's very easy to say, oh, the answer is 1, because those are the 6 numbers, but it's the sixth press. That's very important.
Cool. I saw that Eli did something too, but you're good.
Oh, it's basically the same thing. I think it's the same kind of reasoning. You can also work your way up if you want. You can start from like 2x plus 1, then plug in 2x plus 1 and get 4x plus 3 and keep on going. Do that 6 times and you would end up getting 64x plus 63, so x had to be 0. Doesn't matter which way you do it, you'll definitely get the same answer. All right, on to question number 16. What is the area of the shaded region? So we have, this is a length of 6, and this is a length of 6, but we only know that this is a right angle and that these two sides equal to each other. I think an F5, 45, 90 right triangle, because this is a right triangle and it's isosceles. These two sides are the same. And so actually, I know, I guess you could say a formula for these, but really what's going on is that in general, if this was a side length of 1, then this would have to be a side length of 1 as well. And so by the Pythagorean theorem, this side length squared would have to be 1 plus 1, which is 2. So this would have to be the square root of 2. But I can just shift everything up by a factor of something to get this to be 6, and then these would have to be something else. And well, what is that factor? Well, in order to get something times root 2 to be 6, I just have to do 6 over root 2. 6 over root 2 happens to be, well, you could rationalize the denominator. This would be 6 root 2 over 2, which is 3 root 2. And so it looks like the factor that I want to choose is just 3 root 2 here. So I'll add a 3, and these would, well, 3 root 2 over here, yes. 3 root 2 here, 3 root 2 here, and then this would end up being 6. Okay, so this is 3 root 2, this is 3 root 2, and this is 6. And now I just have to find the area of everything, and this isn't really that bad at all, because I know that this is 6, this is 6, this is just a square, so that's 36. And then I can add back the area of these two things over here. But what's really nice is I can just squish them together. I squish them together and I get a single square of side length 3 root 2. So 3 root 2 squared is just 9 times root 2 squared, which is 2, which is 18. And so I get 36 plus 18, which is, okay, 36 plus 18. It's hard to do this mental math on the spot. I must say 46 plus 8 is 54, right? Yeah, I think so. 54. Looks like option D.
Yeah, so that works.
Awesome.
That works.
Like,
that works. I should say this particular question has another way to do it as well. I wanted to share because oftentimes on the AMC thing they don't have as many things with the Pythagorean theorem, but actually it's interesting. The two triangles add together to 18 and the whole square was 36. So the two triangles add to half of the square. There's a really nice way to see that each triangle is a quarter of the square. If you draw an X, again, I don't have the drawing capability, but if you draw an X through your square, you'll see 4 triangles. Oh, I see Melody's on it. Melody, if you say something, your screen will take over.
Hi. Oh, okay. Yeah, so that's actually really cool. So, just a quick reminder that the problems and the tests are not drawn to scale, so it does not look exact. But since we know that this length of the triangle is 6, and that's also the length of the square, that does show us that each triangle is a quarter of the square, which is another cool way to do the problem. So just immediately after getting that the square's area is 36, you can divide that by 2, and then just add that on. It'll be super fast.
Yeah, cool.
Let's go to the
that
next
was
question.
a very, very nice method. Indeed.
Okay, so a car costs $20,000 in 2021, and then it rises by 25%, rises by another 7.5%, and then decreases by 20%. So a cool thing with percents that like add on to each other is it doesn't really matter what order you multiply them in. So we start with $20,000 car. And then if it rises by 25%, that's like multiplying it by 125 over 100. And then it tells us that in 2023, the price rises by 7.5% of the 2022 price. So it's like taking the whole thing and then multiplying it by 107.5 over 100. And then in 2024, the price decreases by 20% of the 2023 price. So it's taking the whole thing again and then multiplying by 80 over 100. Oh, and here's me working in fractions again. They're just so much easier. I like them more. Because here's a cool thing. If we simplify these fractions, oh, I'm running out of space. Let me make a new slide. If we simplify the fractions, the numbers get so much easier. So we had a 125 over 100, so that's like 5 over 4. And then 107.5 over 100, that's not getting any easier. Sorry about that. And then we have the 80 over 100, and that's 4 over 5. You can see that this 5 over 4 and this 4 over 5 cancel out. You can see it pretty easily with the fractions. So then we have 20,000 times 107.5 over 100. So that's just 200 times 107.5. So you can just do 107.5 times 2 is like, is that 215? And then add 2 zeros at the end. So that gives us answer choice B, I believe.
Yay! And indeed, your fractions are better. Cool.
All right, on to question number 18. A lattice point is a point whose coordinates are both integers. How many lattice points x, y are there such that 2 is less than or equal to x less than or equal to 5, and 2 is less than or equal to y is less than or equal to 5, and the only lattice points on the line segment between 1, 1 and xy, so some line here, is when they're at the endpoint. So there aren't any extra points on the line. It misses all of them very nicely. Okay, so the first thing that I would do here is, well, I don't really understand why we're looking at 2 to 5 and why we're looking at the point 1, 1. And so if I don't understand something, I'll just forget about it. And I'm going to move everything down to where this is going to be the origin and this is 1 to 4, because that's just so much nicer. So I'm going to subtract 1 from everything. And now it looks like 1, that's equal to x, that's equal to 4. And similarly for y. And now it's the point 0, 0. I like the point 0, 0 to xy. So here's xy. Here's the origin. And I want to make sure that there aren't any lattice points on this line. Well, what does that actually mean? Since we chose the origin, which is so nice, the line from the origin here is just, y is equal to the ratio between these two things. I'll call it like y naught over x naught or something, times x. And so if I want the only integers to happen, like the only lattice points to happen at the endpoints, that means that the only time I can get an integer for y is when I plug in x naught for x, the first time anyway. And so it'll be a problem if y naught over x naught is able to be reduced in some way. Because if it's reduced as a fraction, then that means that there's going to be some other denominator that's going to be smaller, and I can plug in that x, and I'd get something that's smaller. So I think that would not work in our favor. Like, for example, if this was 4 and 2, then 4 over 2 would be 2 over 1. And so I could plug in x equals 1, and I'd get y equals 1. And so 2, 1 would be, or 1, 2, I suppose, would be a lattice point, rather than just only 4, 2. And so it looks like I want to avoid any time that I can reduce this kind of fraction. And so rather than counting all the times that I can't reduce them, I might as well count the times when I can reduce them and then, get rid of those cases. Because there's actually not that many. I know that there's, 4 squared in total, because I have 4 options for x, 4 options for y. So 4 squared equals 16 in total. But I have to get rid of the ones that don't work. And what are the ones that don't work? Well, I can go through them. Anytime I have 1, I'll be okay, right? Because I can never reduce anything that has 1 in the denominator or numerator. What if I have 2? If I have 2, then well, okay, if I have 1 or 3 for y, that'll be fine, but 2 over 2 would simplify, and so would 2 over 4, so I have to get rid of those. And again, if I have 3, well, if I have 3 over 3, that wouldn't be good, but 3, 1, 3, 2, and 3, 4 are all fine. And then lastly, what if I have a 4 here? Well, then it's just kind of the same, but in reverse. So I can't have 4, 2, and you can't really see that because of the chat, but you also can't have 4, 4. And so it looks like I can't have this, 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 and this. In total, that's 5. So I take 16, subtract 5, and I get 11, which is option D. Awesome.
Yay!
Okay. And the next question. 2025 consecutive integers sum to exactly 2025. What is the largest integer? Okay. The important thing to remember on questions like this is you can use negative numbers because we definitely cannot do this with all positive numbers. So if they're consecutive integers, well, we have to figure out how many negative numbers we need to cancel out the positive numbers because, well, you're going to have a lot of numbers and it's going to get very big very fast. So let's see, we have 2025 integers. So what I first noticed is once you get to the top, oh, let me figure out how to say this in words. Let's see. So let's say we start at like around the middle. Let's say we're at like 1,010. If we're at 1,010 and then we add on 1,011, that gives us 2021. So that's pretty close, but it's not there yet. But the problem is if we add another 1,012, that's going to get us way too big. So then we have to add a negative 1,010 to get rid of the first 1,010. So we just kind of have to figure out what are the two consecutive numbers that will add to 2025, and then test at the end if it'll balance out to 2025 integers. So if we just divide 2025 by 2, that gives us 1,012.5. So we know that our numbers are going to be 1,012 and 1,013. So we have 1,012 plus 1,013 is 2025. Perfect. And then we'll have 1, 2, 3, all the way to 1,011. But we'll also need -1, -2, all the way down to negative 1,011. So I guess our last thing to do is just to double check that all those numbers, there will be 2025 numbers total. So -1 down to negative 1,011, that's 1,011 numbers. And then we'll have 0, so add another number. And then 1 to 1,011, or let's just add all the way up to 1,013. So 1 to 1,013 is 1,013 numbers. And that does end up with 2025. And I think the best thing to get us started, I know that was a kind of sketchy start, just those numbers popping out of nowhere, but looking at the answer choices is very helpful. So most of the answers are around here, so I just started around there and hoped it was right.
Oh, that's interesting. So you had answer choices, so you were able to work backwards from there. I see Eli has some stuff on his screen too, which might be worth sharing.
Perhaps. I mean, there is a way that you could do this directly. Like you could say, okay, I know that maybe I'm going to start at negative x and go up to x, and well, I can't have more negative numbers than positive numbers because I have to end up with a positive sum. So I have to go like from, say, x plus 1 to x plus k or something. I actually know what that k is because I know how many numbers there are in total. This is 2x plus 1 numbers, and then plus k, so that would be 2025. And anyway, you could like calculate what this sum would be and set it equal to 2025 and solve for the variables. Honestly, it's not that fun. I don't really recommend it. I think just trying to see like what numbers should work, just kind of not really guessing, but just trying to see what would make sense is a much better approach. So probably you should use
Yeah.
Melody's method.
Okay, well, I want to share. Jamie Chen had put something in there, which is an interesting idea. It went in the chat. It's okay. I'll say there was something where he said the average. This is a good idea. If you have 2025 integers, don't worry. 2025 numbers. Don't even worry if they're consecutive integers. If you have 2025 numbers that sum to 2025, well, then the average value is 1. That's super useful. if you know the average value is 1, and you have all these consecutive integers, you can find the last one. So it's because, you got 2025 of them, so there's 2024 gaps. That means that you should go half the gaps up from the average. That would be called 1 plus 1012. And then you get, but I'll say these answers that you guys did here, these methods you guys did here, indeed the answer choices made it much more doable in this way, in this particular way. So that works. Okay, let's continue on.
Let's. Okay. Question number 20.
Oh, one
In
more
the
thing.
United
It is
States-
the untied states.
Untied. Okay, I was about to ask. Yes. In the untied states, the postage stamps are worth 6, 7, and 9 cents each. How many different positive integer cent values cannot be achieved exactly? So one example of something that's not going to be on our list because it can be achieved is 21, because that uses 2 6 cents and 1 9 cents. This is a pretty interesting question. So, well, I think there's some obvious ones that can't be achieved, and that's like 1, 2, 3, 4, and 5, because we definitely can't get anything less than 6. But I can get 6 and 7. Okay, I can't get 8. That's pretty clear, right? Because that's in between 7 and 9, and I definitely can't do anything sketchy there. And then I can definitely not get 10 or 11, because that's before 6 times 6, or 6 plus 6, which is 12. But then from here, maybe it gets a little bit more confusing. So I want to just mention a cool way of doing this, which is not really that useful in this small case where you could kind of just go through everything, but it's just kind of a cool idea to think about. That if I have a number, say, well, let's just say look at 13, because I know that I can get 12. If I can't ever get something like 13 minus 6, 13 minus 7, or 13 minus 9, then I know that this number can't be achieved at all, because I would have to at some point use a 6, a 7, or a 9. So in this case, well, 13 minus 6 is 7, so I know that I can get 13. But if I look at 14, for example, well, that's also on our list. It's just 2 times 7, so never mind. Let's not look at 14. 15, is that going to be interesting? Yeah, probably. So let's look at 15 instead. If I look at 15, 15 minus 6 is 9. Okay, that's also on our list. Never mind. Okay, so we're not going to look at that either. 15 can be achieved. Oh, should have thought about these in advance, but I think 16 can't be, hopefully. 16 minus 6 is 10. Hey, look, that can't be achieved. So if we could achieve a 16 with a 6, then we would be able to achieve a 10. We already know that we can't do that. 16 minus 7 is also 9. Okay, so we can achieve 16. I'm proving myself wrong here. Okay, on to 17. 17 minus 6 is 11. That's on our list. We can't achieve 11, so that means we can't achieve a 17 from a 6. 17 minus 7 is 10. Hey, that's also on our list. We can't achieve a 17 from a 7. And 17 minus 9 is 8. No, it's not. Yes, it is. Oh my God. Okay, 17 minus 9 is 8, and that's also on our list. So we can't achieve a 17 from a 9. Okay, so that means that we can't achieve a 17 at all. And so 17 is going to be the next thing on our list. Cool. Maybe that was a bit too much, but we can definitely achieve, as we saw, 12, 13, 14, 15, and 16. We can't get 17. And then I think something interesting is going to happen from here. And so let's see. Well, we can get an 18, right? That's just 9 times 2. We can get a 19 perhaps, because let's see, how can we get a 19? Well, 19 minus 9 is 10, so that won't work. 19 minus 7 is 12. That can work. So that would mean that we can get a 7 and 2 6s. That would give a 19. And then for 20, let's see. Okay, 20 minus 9 is 11. We can't get that. 20 minus 7 is 13. We can get that, so I know that 20 is going to be on our list. I think it would actually be 6 plus 7 plus 9 in that case. And then 21, let's see, that would be just 3 times 7. 22, let's see, that would be, this one would be 6 plus 7 plus 9, excuse me. So this would be 22 that we can get. And then just one more, bear with me, 23. We can get 23 from, let's see, would that be, okay, 23 minus 9 is 14. So we can get that. Oh yeah, it's just 14 plus 9. So that would be 2 7s and a 9. Okay, 23. But now I'm done. And why am I done? Because I got 6 numbers in a row. Cool. If I can get 18, 19, 20, 21, 22, and 23, then, well, I can just add 6 to all of them using my 6-cent coin, and I can get 24 and 25 and 26 and 27 and 28 and 29. And then I can just do the same thing over and over and over again. And so I know that I'm definitely going to get everything from now on. And so after much explaining, it looks like the only numbers that I won't be able to get are 1, 2, 3, 4, 5, 8, 10, 11, and 17. So that looks to be 5 plus 1, 6, 7, 8, and 9. That looks like option B to me. Okay. Are we correct here? Looks like we are.
Yay! Actually, the best part is if you haven't been able to tell by now, Eli's just doing them as he sees them. We're trying to show you that this is how you solve a problem if you haven't seen it before. And this is indeed a good way. Let's keep going.
Okay, the next question. How many positive integers are factors of 2025? Oh, a cool rule, I guess, is if you get the prime factorization of a number. Oh, actually, I'll just show you. It'll be easier. Let's prime factorize this number. So 2025, oh, a cool thing you should know about the next year is it's a square year. Math problems really like to use the year in the problem. So 2025 is 45 squared. Very cool. So that's 3 squared times 5. So the prime factorization of, oh, that feels kind of weird. I don't know why. So the prime factorization of 2025 is 3 to the 4th times 5 squared. So here's the cool trick. If you have the prime factorization of a number, you can find just how many factors, or yes, how many factors, total factors, by just adding 1 to each power you see and then multiplying them together. So we have 3 to the 4th, it's to the power of 4. So we add 1 to get 5. And then we have 5 squared, so that's to the power of 2. And you just add 1 and get 3. So 5 times 3 equals 15. So it has a factor, or it has 15 factors. So should I explain why this rule is, or
No, that's good. I think just because of time, we probably are a bit short. But I'll say that's something we teach, and so we also happen to run an online school. But wherever you learn all of these things, if you do these kinds of math things, you'll find the lesson explained to you. But with that, let's go on because there's some more questions that are there.
All right, on to question number 22. If 4 congruent circles are drawn in the plane such that every pair of them intersects in exactly 2 points, what is the smallest possible number of points that lie on at least 2 circles? And I think it's very important that they're congruent here, because I was just imagining that maybe you could have them like nested in each other and stuff. But no, they're congruent circles, so we can't do anything fancy like that. But I think even so, there's going to be maybe something interesting that happens here. But first, it doesn't really matter what picture I start with. It has to look something like this. The 2 circles are just intersecting. It doesn't really matter exactly how this looks. But now I guess I have a choice of where I put the 3rd circle. But there's really only one thing I can do to minimize the intersections, right? I can just choose one of these intersection points. And the reason I can't do both at the same time is because, again, they're congruent circles. If I had a bigger circle, I could do something that goes through these 2 and then wraps around like this, but I can't do that. And if you wanted to see for yourself that I really can't use the same circle on these, you could imagine maybe this is a chord or something. And then, if I had to fit a circle of a certain radius around this chord, then really I only have 2 choices. I can go in this direction or I can go in this direction, and there really isn't anything else I can do. So it has to be just using one of these intersection points. And so I'll probably just choose this one because that looks nice. And I get a few more. Well, this is the same intersection point. This was already there, but now I get a new one here and a new one here. So I get 4 intersection points in total, but now I can do something really fancy. And that's if I happen to reorganize this diagram a little bit to be more symmetric. Then I can actually choose my last circle to be this circle that goes through these 3 points. And so I said it didn't matter before, but actually it does, because I have to make sure that the proportions are all correct in terms of where these intersections are happening in order to place this last circle ever so gently with these 3 points here. And so when I do that, then actually these 3 points serve as the 2 intersections for each of these other circles paired with this blue circle, right? It's these 2, and these 2. And so I actually don't add any more intersection points. I just get those 4, and it looks like option A to me. But I think it's very easy to go wrong and end up with maybe 5 if you don't see this magical circle here.
Yeah, so this particular one, it turns out if you really draw it very carefully, the scale, and draw a perfect three-circle Venn diagram, it actually will work exactly. So the thing about this is if you don't draw it to scale, it doesn't look quite right. But it's easier if you actually literally try to draw a three-way Venn diagram and you look at all of the angles, everything works out. We have a few more questions to do, so I think we'll go on forward from here, but good for you.
Here's another problem. A standard 20-sided die is an icosahedron where all faces are congruent triangles. How many edges does it have? Well, it would be really hard to count all of them, especially because you can't see some of them. So let's find the cool trick for this. So we know that there are 20 sides, and each side is a triangle. So that has to tell us something, right? So a triangle has 3 sides. So then if we have to find the edges, we can see each edge is a side of a triangle, and each edge is also shared by 2 triangles. So we have this triangle and this triangle both share that edge in the middle. So then we know there are 20 triangles, and then so let's see what we can do about that. So each triangle has 3 sides, and there's 20 triangles. So we have 20 times 3 equals 60 triangle sides. But each edge has 2 sides of a triangle, I guess, because they're on one edge. They're shared. So 60 divided by 2 equals 30. So that's 30 edges. So that was a lot easier than trying to count all 30 in this picture. And our answer is D, 30.
Yay! I will tell you, when I was making that diagram, I very intentionally turned it in a way where the edges seem to overlap with each other. So I tried to be as mean as possible. Because if you try to count the edges, you will get it wrong. All right, let's keep going.
All right, on to question number 24. And this is a really, really fun one, especially if you happen to like chess, or even if you don't. What's the largest number of knights that you can put on a chessboard so that no knight can attack any other knight? And recall that a knight can attack squares in like this L shape, right? You know, move over 1 and then down 2 in any direction. So looks like this. And there's actually kind of a fun trick going on here, and there's also some cool like graph theory math in the background. There's something called a bipartite graph that this creates on the squares of a chessboard, but that's not really important. But the idea is that you can see from where the knight is standing. It's on this, I guess, yellow square. Traditionally, it's like white squares and black squares on a chessboard, and it's attacking only these non-yellow squares, the black squares, I guess. And so that means that if I place them all on the white squares or the yellow squares here, then they won't be attacking anyone else. And so if I just place them all on the yellow squares here, then I can have, well, there's 64 squares total. 64 divided by 2 is 32. And that's a lot of knights. I think it's probably just fairly clear that I can't do any better than that. But if you wanted to prove that to yourself, then one thing that you can do is go ahead and like start actually pairing them up, which is kind of the bipartite thing. So if I pair up like this and this as the first one, and then I don't know, like this one and this one as the second one, and I just do that for the entire grid, then I'll end up with all 32 pairs, so 64 squares in total. And what this means is that I can only place a knight in one of these 2 squares, right? Because I can't possibly place them in both because they would attack each other. And so since I did that for all of the chessboard, that means that I can't possibly do better than that because I've literally just proven that I can only choose one of each of these. So that means I can do at best 32, and I can definitely do 32 because of the nice light square magic. So looks like our answer is D.
Yay! And I see that people like chess in the chat. So that's very nice. This particular question, I just got curious about it myself, and I'm happy that you guys all figured it out too. The last question.
Oh, yeah.
We can work
Let's
together,
do
maybe
that.
we'll see.
Oh,
But go ahead. Melody,
yeah.
you can start. Yeah.
The last question is very tricky. So observe that 12 squared equals 144 and 21 squared equals 441. So the original number is reversed and the square is also reversed. So we want to find how many two-digit numbers there are that do that. So Z doesn't end in 0, so we can't have like 20 and then 02, which doesn't work anyways, but it's okay. Okay, so we want to find the total number of numbers Z. So let's say that Z is like big X, big Y. So actually 10X plus Y, just to split it up, because that just makes everything easier. So let's see. If we want to find Z squared, that would be 10X plus Y squared equals 100X plus 20XY plus Y squared. So if we want it to be like the example from the problem, like 12 squared equals 144 and 21 squared equals 441, where the square is a three-digit number and we just reverse it, we want to make sure, oh, I missed the square, sorry guys. We want to make sure that x squared is one digit and y squared is also one digit. And in the middle, let's make this a 10 times 2xy. So we have like the hundreds place, the tens place, and the ones place. So we want to make sure x squared is one digit, y squared is one digit, and 2xy is also one digit. So we know that x and y have to be 1, 2, or 3. So then we have to check that with the 2xy portion. How do we, I guess we could just try them all. There aren't that many numbers. So we know that 1 and 1 definitely work. 1 and 2 work. 2 times 1 times 2, that's 4. So we know that 2 and 1 also work. 1 and 3 work. 3 and 1 work. What else works? Oh, 2 and 2 works. I don't think anything else will give us just a single digit for these. So it seems like there's just 6 possibilities, but there's another problem that's like haunting me. What if there can be a 4-digit square that also reverses? So
Ooh,
that
cool. So first of all, this is a really hard question. And so what you got is you got all of the three-digit ones. So then you got 6. So that's good. And then now the four-digit one is actually hard to go and analyze out. But so first of all, that is the answer. It is 6. But the thing that's haunting you, that let's see if we can do this one together. Because again, I can't draw, so you guys maybe can help draw out the ideas. The interesting thing is if I have a 4-digit number, you know, you have these, like, you wrote them as 10x plus y, or Eli's writing 10a plus b, it's all the same. If you add the square and its reverse, that would be your 10x plus y whole thing squared, plus a 10y plus x whole thing squared. The reason it's interesting to add the number and its reverse is that if I have 4-digit numbers, if I add the 4-digit number and its reverse, I always have something divisible by 11. See if you can figure out how to, see if you guys can figure out how to explain that. Like, there's an interesting fact, which if I take any 4-digit number, like you're talking about 4-digit squares, right? So there's an interesting fact that if you take any 4-digit number and add its reverse, you can actually prove that that's always divisible by 11. See if you guys can like collaboratively get that, because that would be really useful.
Okay, I think I see what's going on there. Yeah, if you start with a number like ABCD and then reverse it to DCBA, I think there's probably a few ways that you could view this, but I think that the easiest way is just to notice that, well, this is just like 1000A plus 100B plus 10C plus D. And then the reverse of that, well, I'll actually write it in reverse, is going to be 1000D plus 100C plus 10B plus A. And then, well, if I add them like this, then I get 1001A, and then 110B, 110C, and 1001D. Okay, so here we go. And so that means that, well, if 1001 and 110 are divisible by 11, then so is the whole thing. And it just so happens that they are. We actually looked at 1001 earlier, and 110 is just 11 times 10. So everything here is divisible by 11, which means that if I add these two things, it's definitely divisible by 11.
Cool. So now that proves that. So going back to Melody's thing, you have the 10x plus y whole thing squared plus the 10y plus x whole thing squared. That's got to be divisible by 11. See if you can start using algebra to narrow stuff down.
Well, so let's expand these again. So we have 100x squared plus 20xy plus y squared. And then we'll have 100y squared plus 20xy again plus x squared. And combining like terms, we'll have 101x squared plus 40xy plus 101y squared. So there are no nice super cool factors of 11 here. So we kind of just have to work and see if it's possible at all to make this a thing.
Yeah, I'll give a hint. It turns out you can sometimes reduce modulo 11. Because if it's supposed to be divisible by 11, then you can subtract multiples of 11, and that's still supposed to be divisible by 11. You can actually either add or subtract multiples of 11.
So that'll definitely make things easier. I think Eli started it on his
Yeah,
screen.
Eli, what do you
Would
see? Eli's got something going. It's still not obvious from here, but Eli's got a good start.
Well, one thing that you can do is 101 is 99 plus 2. So I can take out my 99x squared, and well, that's definitely going to be divisible by 11. So I can just look at my 2x squared and my 2y squared, because that's what's kind of left that may be stopping this from being divisible by 11. And I can do a similar thing with 40. I think maybe what I'll do is actually the reverse, because 44xy is divisible by 11. And so actually this is 44xy minus 4xy. And so the minus 4xy is what's kind of stopping us from being divisible by 11 potentially. And so now I get something that looks really, really nice. I think maybe some people will see where this is going. I certainly do now, although I did not before. This is very cool. Melody, you want to take it from here?
Ooh, okay. Let's make this even simpler and just factor out some twos because I like small numbers. So minus 2xy. And then you can factor this. So this gives us, this is x minus y squared, I think. So we need
Yes.
this whole thing to be divisible by 11. And, well, you can't really have that unless x equals y, I guess. So x has to equal y, which if we remember what our x and y mean, that's just like the digits are the same. So it gives us like 44, 55, 66. I think if we just test that, it doesn't work out very well.
Yeah, that's the way to finish.
Definitely not reversible.
Yeah, so that's the way to finish. I mean, it will take a while to actually go and test some of those out, but exactly right, because it would be enormously painful to try all of the squares, all of the 4-digit squares. But what you did is you just narrowed it down to like 44 squared, 55 squared, 65, 66 squared, and so on up to 99 squared. And they just don't behave well. Like it would be crazy for, well, you would basically need that square to itself be a palindrome, right? Because that's the only way it would work. Because when you reverse the number, like 66, reversing 66 is 66. So you'd actually need that 66 squared itself was a palindrome. Okay, yeah, but this was the hardest question on the list. I tried to be nice by making 6 like the biggest reasonable answer, and then there was a 13 that jumped all the way out there. The 13, if you want to know, is a trick answer, which was my first answer. I got it wrong because the 13 is when you notice that, oh, x equals y, bam, let's add the 44, 55, 66 all the way to 99. That would give you actually the 13, which is the wrong answer. But yeah, with that, this was fun. We actually finished like right on time. Whoever's spotlighting, could you put all 3 of us on if there's any chance? Thanks so much. But I just wanted to say thank you, everybody. It was nice to get to know all of you through this live solve. And wow, it's always a great pleasure to be able to work with extraordinary people. If you like the way this went, actually the problems are available from our site. Actually you can get them through our site. We're live. This is live by Po-Shen Loh, live.poshenloh.com. Also, if you like the way that this whole teaching thing was, well, you can learn from Eli, Melody, people like them every week. We have a model here where we go and find extraordinary people like who you just saw here, and then we run live streamed math classes. So With that, good luck to you on whatever you're doing. Good morning or good evening, wherever you are. Pleasure talking to you all. Bye-bye.
Bye.
Bye.